This video is for Review Quiz Chapter 4, and this is all about linear regression. So here we have some data, and it's comparing commute time to their score in a well-being test for maybe like health insurance or something. And we're asking here, which variable is the explanatory variable, and which is the response variable. So if the well-being score is the explanatory variable, then that means the well-being score will affect the commute time. And though that could be the case, we would expect the commute time, right? This is a time. It's not really affected by anything else besides like maybe your choices on where you're living, which could come from the well-being score. But it's reasonable to assume the commute time is going to affect the well-being score in a much more dramatic way than vice versa. So the explanatory variable should be commute time, and the response variable is a well-being score because commute time affects the well-being score. Okay, draw a scatter diagram. Let's go ahead and open this in StatCrunch. Scatter diagrams are fairly easy to do. We're just going to go graph, scatter plot. The commute times are explanatory, so it should be our x variable. The y variable will be the score. Let's just compute that. And there's our scatter plot. Note that this is not 0, 0 at the origin. It's at 64 and 20 because it's way further up past 0, 0. Okay, that looks like C, I believe. Yep. All right, and linear correlation coefficient, let's go ahead and use stat, regression, simple linear. Once again, our explanatory variable is going to be our x. The response is the y. And I'm going to save the residuals here just in case we need them. Okay, compute that. You go on the second page, you can see how the what the computer thinks the line of best fit will be. And going back here, we can see that it has the correlation coefficient already calculated for us right there. So we don't have to do any calculations by hand. Negative 0.9882. See, once 3 places, yeah, so negative 0.988. And yes, there does appear, right? The critical coefficient, right? This has 1, 2, 3, 4, 5, 6, 7 values. I mean, no matter what you're looking at here, most of these values are much smaller than this, right? 0.98 is such a high correlation that it definitely seems there'd be a negative linear association. It's not going to be positive linear, right? It's negative. So there's going to be a negative linear association. That does mean that it's linearly associated, but it's just in the negative. So as the commute time, or sorry, this is, as the commute time increases, the score decreases. That's what the negative linear means. Let's check that. And that's correct. Okay, the next problem says researchers wondered whether size of a person's brain was related to their mental capacity, or the MRI to IQ. They selected 5 females and 5 males, and here is the data. Okay, draw a scatter diagram for everything. So let's go ahead and I'm just going to copy this. See if I can do that. Yep. And copy this. It doesn't want separated between male and female. They wants just everything. So I'm going to copy the male and the MRI and the IQ over so that we have all the values in one column in each one. And that's going to allow us to do a scatter plot really easily. I mean, the female MRI and the female IQ, even though it says female, it's actually for everyone. That's how I've done it. Compute that, and there's our scatter plot. Okay, which one looks like that? I think it's A. No, it's going to be C. Yep. 140. A had the axes flipped. 140, that looks right. Now compute the linear correlation coefficient for this. Well, that's going to be the same thing as just doing stat, regression, simple linear. And even though it says, again, female, we're going to assume the MRI is the explanatory variable, right? Because the brain size should affect the IQ. That's what we're testing to see here. So MRI is going to be the explanatory, or the X. IQ is going to be the response, or the Y. Let's compute this, and here we go. We have our correlation coefficient is 0.6588 for a sample size of 10. Sample size of 10 is 0.632. 6588 is greater than 632, so yes, they are linearly related. You wanted 3 places, so it should be 659. Yep, 659. And once again, that is greater than the critical value of 632. Okay, now we're going to split it up over gender. And to do that, what I can do, I'm going to go ahead and delete these. And then I can go graph, multiplot. That allows me to plot multiple sets of data on the same graph. The first one's going to be the female explanatory, the female response, and I'm plotting the points. So we're going to add that. That's the first plot. The second one's going to be the male version of that. And add that. Then hit compute, and there we go. We have the females are in blue, the males are in red, and we can find the graph that best represents that. So we know the male red is going to be these top 3 and these 2 down there. And that's going to be in the blue circles are male, so that looks to be the correct one. An A. Yep. Okay, now we can do linear coefficient, and for this, let's just do each one individually. So we'll do regression, simple linear, female MRI, female IQ, compute that. The linear coefficient is going to be 0.5412. 3 places, so 0.541. And doing the same process for the male MRI and male IQ. Correlation coefficient of 0.655. And both of these have 5 for n. So 5 for n means that the critical value is 0.878, and both of these are lower than that. So we know that because the correlation coefficient for females is positive, and the absolute value of this is going to be 0.541. This is not greater than 0.878, right? 0.878 for n. We would say no relationship, at least no linear relationship exists between the MRI count and IQ for females. And again, for the male one, it's going to be positive. The absolute value, this is again 0.655. This is not greater than the critical value, same critical value of 878, because again, we have five data points. There is no relation between those two variables. And that's all correct. All right, for question 3, we have 4 data sets, and we're asked to compute all the linear correlations and then graph them. So open these in StatCrunch. So let's do stats, regression, simple linear. Do each one individually, x1, y1, compute that. And we have a correlation of 8164. Okay. Stat, regression, simple linear. x2, y2, correlation of 8169 or 817. Okay, third data set. Regression, simple linear, x3, y3, and y3 there. Compute that. We have a correlation coefficient of 816. I guess you're seeing a pattern here. 816. And finally, stat regression. .817. Okay, so now we wanted to do scatter diagrams for each one of these sets. So the first, second, third, and fourth. Graph. We could do multiplot. Maybe that'll be easy to see. Let's just try it. X3, Y3, X4, Y4, and compute that. And there we go. So this has, make it smaller again. The blue dots are X1, Y1. They're not quite clear on this. Let me get rid of two of them, make it a little bit more clear. The blue dots are kind of in this pattern. The red dots are very clearly this one right here. So I think that's, see, 0 to 15, 0, 15. This doesn't go really higher than 10. Yeah, that looks correct to me. And then we know this one's clearly this quadratic behavior here. Okay, let's plot the next two. Okay, x3, y3 has this linear line and this dot right up there. Looks like this one. Yep. And then the fourth data set has this vertical line, this dot way over there, which looks like B there. And that's all correct. So what does this tell you? That this tells you that you cannot just rely on the correlation coefficient, right? These all had about the same correlation coefficient, but the graphs were wildly different. This is definitely not linear. This, I mean, it looks like the correlation coefficient works, but this is clearly quadratic, the way that looks. This one's fairly linear in this way. There's that one little outlier there, but I would say that's fairly linear. And then this one's linear in that it looks like a vertical line with one outlier, but that's a separate kind of thing that you're talking about. In this case, we are looking at drawing these stuff and then plugging in the finding the equation of best fit. That's what we're looking at here. So let's go ahead. We don't have to do this by hand. We can use StatCrunch to do so. So let's open it this way and then do graph scatter plot X and Y go into their slots, and then there's our scatter plot. Kind of this little bit of a bowed shape there, but that's what it looks like. Again, this is at 30, about 80, 30, looks like this one right here, C. Okay, find the equation of a line containing the points 40, 77, and 70, 52. So 40, 77 and 70, 52. Now, to find the equation of a line that goes through these 2 points, we just use the point slope formula of a line, where x1, y1 is one of the 2 points that we have here. It doesn't matter which one, just choose one. I'll just choose this one. Again, it doesn't matter. We have to know what m is, though, and m is going to be the slope. The slope is going to be y2 minus y1 over x2 minus x1. So we need 2 points for this. So I'm going to name this one x2, y2. And now I can find the slope. Just plug the things in. So y2 is 52, y1 is 77, x2 is 70, and x1 is 40. So calculating this, we're going to get, let's see, that's going to be 25, negative 25 over 30, or negative 5, 6. And then now we can go ahead and plug in y1, m, and x1 into this equation. So y1 is 77, m is negative 5, 6, and x1 is 40. The x and y in this equation here, those must be kept as x and y. Sorry, that's the x and y. Those that you need to have variables in the equation for there to be a line. So you have to leave them as x and y. Okay, we can simplify this by just distributing this one. I'm going to add the 77 over as well. Negative 5, 6x minus 5 times 40 is going to be, it's going to actually be plus because the negative times negative cancels. 5 times 40 is 200 over 6 plus 77 over 1. So we're going to multiply this by 6 over 6. Let's get a calculator for this. 462 plus 200. So we're going to get y equals negative 5, 6x plus, what was it? It was 662 over 6. You can, of course, reduce that. (662) divided by 2 is 331. Over 3. I just reduced the top and bottom by 2. Okay. That should be what we're looking for there. As long as I did it correctly. We want 331 over 3. Okay, now we're going to graph the line. Really, this is just going to be the line that's going through, let's see, 4077 is the second data point, and 7052 is the last one. So we're looking for a line that goes through those 2 points, and that fits this data set here. And that looks like part C. Part C goes through this line, the second line, and this last line there. Okay, now by hand, again, no need to do it by hand, or just use StatCrunch to calculate the least squares regression line. So we have our data already. Now let's just do the simple linear regression. Okay, our line here is negative 0.72. And our y-intercept is 105.6. Okay, I can just, it's already plotted it, so I can just look at this graph to see what it looks like. You see, it almost hits the second point, but it does not hit this third point. So that's going to be, looks like this one right here. All right, compute the sum of the squared residuals for the line in part B. Now, this is going to be easier because we don't have this. I'm actually going to save the residuals from this. So I think we're going to need it for this next part. But for the square residuals in part B, we're going to need to graph this line. And I think the easiest way of doing this is to actually, I'm going to copy it to clipboard and then graph this, just hit Control C, and graph this in Desmos. So let's go ahead and do that. So here I'm going to go to the graphing calculator. And if I paste the data, yep, it gives me a table already because of the Desmos understands how to read it. Okay, now we know we have a line. The line is y equals negative 5/6 x plus, what was it? 331 over 3. And you can see it does indeed pass through those 2 points. Now, the sum of the squared residuals is going to be the height of the distance between the point and the line, but that height's going to be squared, and then you're going to add all of them up. So this distance here is 0 because that line goes through that point. The same thing is true for this one. So really there's only these 3 points that we need to calculate the residuals for. We already have the line. Now I'm actually going to use function notation. It makes it easier to calculate here. So if I do f of, and we're looking for x value of 30, f of 30, I think it was 85.333. That's what this value is here. If I can get it exact, there you go. 30 is 85.3333. That's the height. And the distance between these 2 points is just the difference of the y values. So we already have this y value, 85 point that, and then subtract it off of this height, which is 82. And this needs to be squared because we're going to sum the squared residuals. So there's the residual and it's squared. Just square it. There we go. So that's the first residual squared. Let's find the next one. The next one is going to be an x value of 50. So we're going to do f of 50. That's the height of the line. And then the height of the point is going to be 72. So I can subtract 72. It makes it negative. But that doesn't matter because if I square it, it'll always be positive. It's the same thing if it were positive or negative squared. So that's the height of the second residual. This third residual, same process. Let's see if I can get it on there exact. There it is, 60.333 repeating. And the height of the point is 65. So we're going to go f of, was it 60? Yep. Minus 65. That's the height of this point. F of 60 is the height in the line. And then we're going to square that. Square it, not to the 6th power. Okay, so now we have all of our squared residuals, and we want to add them up. Now, of course, you can just go 11 point plus 11 point plus 21.7777. Kind of a clever way to do this is to give these variables. So a equals, b equals, then c equals, and then all we need to do is do a plus b plus c. And here it tells us that the answer is 44 because this is more exact the way that this is read. So 44, of course, you can see 44 here when you add them up. That rounds to 44. So that's the sum of our squared residuals for our problem. Now, the sum of the square residuals for the least squares regression line, We can, of course, go to StatCrunch. I have actually saved the residuals. I can square them by doing data, compute, expression. If I take the residuals and then square them, that's going to square all these numbers here. Just squaring them gives us this. And then all I have to do is add them up. Expression. Let's do the sum of the residuals squared. And that gives me 26.8. That ends up being the exact same thing as, if you scroll down here, when you do the simple linear regression, sum of the squared residuals, that's what this is, and 26.8 is the error measurement. That's how far the line is off of the points, sum of the squared residuals. So 26.8 is the exact same answer that I calculated here. That's what we're looking for. And so you can see that the least squares regression line gives us a smaller squared residual or error measurement. That's how far the line is off of the data points, than the one that actually meets two data points that we by design, right? This line here hits two of these data points, 4077 and 7052. But even though it hits those two, it doesn't lower how far the error measurements are of every other point. That's the reason why the least squares regression line, this is a better fit to the data. So the line in part B passed through the most points. The line in part D minimizes the squared residuals, thus being the best fitting line. And that's all correct. Okay, question 5. Is there a relationship between the child's height and the head circumference? 11 children from our practice measures the height and head circumference and gets this data. So let's find the least squares regression line. Same process we've been doing. Stat, regression, simple linear, x and y. I'm going to save the residuals just in case. And the least squares regression line here, I think it's a little bit bigger, is 12.85. We want 3 places here. And that constant to 1 place. Okay. So we're going to do 0.169, so 170x. And the constant to 1 place, this is 12.85, so 12.9. Okay, interpret the slope and the y-intercept if appropriate. So the slope says 0.170. X is going to be the child's height and y is circumference. The slope is y over x. So it's head circumference per child height, or x is going to be, does it say x is height in inches, y is head circumference in inches. So it's going to be inches height, so it's going to be a head circumference in inches per inch in height. That's what the slope means. X is always in the bottom, so it's going to be per whatever the x unit is, so x inches in height. So for every inch increase in height, the head circumference increases, because the slope is positive, by 0.17 inches on average. That's the slope. Now the y-intercept, for the y-intercept, we are asking what happens if x is 0. In other words, the child's height is 0. But a child's height can't be 0, so it's not appropriate to interpret the y-intercept. Okay, use the regression equation to predict the head circumference of a child who is 24.5 inches tall. In other words, plug 24.5 in this equation here. This is easiest done on Desmos. We can use this calculator actually. I mean, this whole portion of the slide is just a scientific calculator. So if we have our function 0.170x plus, what was it? It was 12.9. Then all I have to do is plug in our value that we want. The value is 24.5. And so it's saying that our head circumference should be 17.065. 65 is going to be 17.7. Yeah. Okay. Compute the residual based on the observed head circumference. So what's the difference between this and the actual data? Do we have data for 24.5? We do. 24.5 is 16.8. So the residual is the difference in the heights. So 17.07 minus 16.8. And the residual is 0.27 inches. So that's the difference between the observed and the model. The residual for this observation is 0.27. And the model, it was 17.07. That was higher than the actual, meaning that the actual is below average. That's the idea. The head circumference of this child is below the actual predicted value. We predicted 17, it actually was 16.8, so it's below the average that we predict at the very least. Okay, now we're going to draw the least squares. This is easy to do because StatCrunch already did it right there. Okay, let's graph that. It's not this flat line. It's much more shallow than this line is here. What's the difference between A and C? A is this. Okay, this line is higher up on C than it is on A. And it should be close to this point, almost close to that one, which looks like this one right here. So that's going to be C. A looks to be too low. Yeah, it's not as close to those data points. So C is the correct one. Notice that the two children, and I'll just show this again. The residual here is what I calculated. That's the height. That's the 0.27 inches there. Okay, notice that two children are 26.75 inches tall. How can this be? The only explanation is the difference in the fact that there's no reason to assume that. Was that even said anywhere on here? No. For children with a height of 26.75, head circumference vary. There's no logical explanation. No, it's most likely the head size vary. Because it's real life. I mean, obviously things are going to vary. They're not going to be exact. Would it be reasonable to use the least squares regression line to predict the head circumference of a child who is 32 inches tall? I would say no, because the height is outside the scope of this model, right? The model only went up to a maximum of 27.75, it looks like. Yeah. So we can't really determine much outside this range of values here. Just like x equal to 0 doesn't really make sense, even though it has a 0 value according to the model. So it's outside the scope, therefore we cannot extrapolate this data for that. Okay, let me see what I did wrong here. Give me just a second. Okay, the only error that I had here was this one right here. The residual for this observation is not 0.27, but negative 0.27. That's because the actual data was lower than the estimated line that you can see right here. And because this is a downward, right? We went down from the line. That means it's going to be negative, not positive. It's still calculated the same way. You still do the difference there. I just did it the wrong way. I was thinking about the sum of square residuals. That's why I didn't think about the negative or positive. But if we check that answer, we now have 100%. Okay, moving on to the last problem. And the biggest factors in determining the value of a home is square footage. Okay, we know we have a square footage in thousands of dollars, and we have our housing data right here. So the explanatory variable, says square footage explains the value of a home. So square footage is the explanatory value. Draw a scatter diagram of the data. Let's plug it into StatCrunch. Graph, scatter plot, X is square footage, Y is selling price. And there's our scatter plot there. That looks to be A. Yeah. Yeah, I think it's A. Okay, linear correlation. Well, let's go ahead and do stat, regression, simple linear. X for X, Y for Y. And our linear correlation is 0.884 for three places. And is there a linear correlation between square footage and asking price? I think the answer is yes. There's no critical table here, but this is very high linear correlation. So I would say yes. Least squares regression line, well, once again, this is right here. 0.15, let's see, what does it want? It wants 3 places, the intercept to 1 place. Okay, so the slope is 0.53. And the correlation, or the constant is 22.6. Okay, interpret the slope. So once again, slope is y over x. Y is selling price, x is square footage. So it's going to be thousands of dollars of selling price per square foot. So for every additional square foot, the selling price increases by $0.153 thousand, or in other words, $153 on average. Okay, is it reasonable to interpret the y-intercept? A y-intercept has an x value of 0. 0 is 0 square feet, but no house can have 0 square feet. That's not a house. That's nothing there. So no, a house of 0 square feet is not possible. It's not outside the scope. It's just not possible. Okay, one home that is 1417 square feet is sold for 210,000. Is this above or below the average? So, let's take this data into Desmos. Go ahead and graph what we just found. 153 plus 22.6. And it's asking us square foot of 1417 sold for 210. So if we do f of 1417, we get an average price of 239.041. So 210, sorry, x of 1471 is like right here. And that gives us about a price of 240. So if the actual point, right, for 1417 was 210, you can see that that's way below what the average would be. So that residual will be negative. So the home price is below average. The average price is, round to the nearest whole number, 239. Okay, let me see if I made a rounding error somewhere. Okay, it wasn't a rounding error. It was just they wanted is not possible and outside the scope of this model. I don't know why the outside the scope of the model matters, because it's just not possible. Like, there's no point in looking at that, but that's what it wanted. It's still 0, and if you check the answer there, it's 100%.